Welcome back, 8th graders. This is question A3 for the School of Rocks. Of course, we're trying to figure out big idea A and our place in history, and whether or not we're tiny or we take up a big piece of that. The third one here is, how can we even tell how old a rock is, assuming that no one was even there? So I think we'll just talk you real quickly through this Prezi of how it is possible to date a rock. So if you recall, we've looked at some layers here, and part of it is really easy. It's known as the law of superposition, and that is, if you see a series of layers, that you can assume that the bottommost layer formed first, and then the next layer on top formed second, third, and so on. Because obviously you need these layers to form first in order for the rest to form on top. And of course this fault right here through here shows you yet another feature too. So that's one way, but that's known as relative dating. And relative dating is good. Law of superposition is very useful, but it doesn't tell us an exact age. So what we really want to know is the exact age. Is it possible to know, like with numbers, how old a rock is? And it is actually possible. It takes a little bit of background knowledge in, believe it or not, atoms. And so this is where your knowledge of atoms and us reviewing it with star stuff will come in kind of handy. Of course, this is the periodic table of elements. Every atom that exists is represented on here. Every one has an atomic number. Like hydrogen has an atomic number of 1, helium 2, lithium 3, and so on. And of course, the atomic number is the number of protons in that atom. If you have a carbon atom, it's different from nitrogen because carbon has one less proton and nitrogen has one more proton in it. And that's important because there are some atoms that are unstable. And those unstable atoms, that's what gives us the possibility of being able to figure out how old a rock is. So there's this video clip that talks about unstable atoms. So I'm going to let that play for you so you can understand it.
The nuclei of most atoms stay like this forever, but radioactive nuclei are unstable. They're like pieces of popcorn waiting to pop. Once in its life, a radioactive nucleus decays and throws out part of itself as radiation. Some atoms throw out a pair of protons and a pair of neutrons together as a particle. This is alpha radiation. In another nucleus, a neutron might suddenly change into a proton, throwing out an electron at the same time. This is beta radiation. Gamma radiation is an electromagnetic wave with very high energy. It's sometimes given off by a nucleus which has just decayed in another way, as the nucleus struggles to make itself stable. Atoms of the same type always decay in the same way, so it's often possible to work out what type of atom is involved by detecting and measuring radiation. The radiation is a telltale clue to the atom which created it.
So as you look, then, atoms tend to fall apart, at least the unstable ones, they're radioactive. That's what makes them radioactive. So losing protons and neutrons is what makes an atom unstable. Now, how we can do that, or how we can use this to help us tell time, is right here. When protons are lost, the atom changes. So atoms flip from something unstable to something stable. Uranium, for example, loses protons and it converts into something more stable, like lead. And so, if we just know how slow or how fast something changes, these atoms, we can use it as a clock, a way of telling how old a mineral is, by how much it's changed, how much of the uranium has fallen apart and turned into lead. Kind of like with this video right here with Michael Jackson getting older and older. So if we were to go and look at this in more detail, what this really means is this: radioactive atoms decay into stable atoms. Each atom has its own rate of decay. So this is kind of like a math problem. Some minerals have radioactive atoms in them. So if we can find minerals that contain radioactive atoms, we count the number of radioactive parent atoms, the crazy unstable ones like this, and we compare that to the number of stable daughter atoms, the more normal kind. And when you do that, then that allows us to figure out how old the rock has been there. Because the longer it's been around, the less of the unstable radioactive parent we find and the more of the stable daughter element we find. So you can use radioactive atoms, you can use radioactive decay to figure out the age of some rocks. There's this thing known as half-life, which is the amount of time that it takes for half of the radioactive atoms to decay and decompose into stable atoms. And all radioactive elements have different half-lives. So for example, carbon-14 has a half-life of only 5,730 years, whereas rubidium converts into strontium, and it takes 50 billion years for half of that to convert over. So if you can find the right radioactive element in the crystal and measure how much of it is there and how much of it has changed, you can calculate how old that rock is. And so that's just one example of how rocks talk to us. In this case, they talk to us and tell us how old they are. So that's a quick review, a brief one, and that covers A3 and really helps us to kind of unpack and uncover and figure out what our role is in the history of the Earth. Are humans a big deal? Are we big or are we tiny in the history of the Earth? So best of luck to you, and maybe I'll see you over in the Big Idea B section when we review those. So best of luck. Bye.